Hey everyone, welcome back to Neural Network Lectures. In the last class, we have learned about error correction learning and memory based learning. And also, I introduced you to Hebbian learning, right? So, without wasting time, let's move on to Hebbian learning. Okay, Hebbian learning mechanism. Hebbian learning mechanism is one of the oldest learning rules. It was proposed by Donald Hebb, Donald Hebb in his book Organization of Behavior, Organization of Behavior in the year 1949. Okay, so he postulated that suppose there is a neuron A and there is another neuron B. Okay, if A is near B and A fires B or excites B continuously, then metabolic changes will happen in both the cells A and B such that A's efficiency to fire B will increase. Okay, so in simple terms, if A fires B repeatedly, then its ability to fire B also increase. Okay, this is an actual phenomena happening in the hippocampus of our brain when we learn something new. That is the reason why I said that Hebbian learning mechanism is very similar to the physical changes that happens in our brain when we learn something new. Okay. However, Hebb's postulate is based on a neurobiological context. So how do we translate it to the way we need, that is, to implement in an artificial neural network? It can be done by breaking the postulate into these two simple rules. That is, if two neurons on either side of a synapse are activated simultaneously or synchronously, then the strength of that synapse is selectively increased. That means if we have a presynaptic neuron J and a postsynaptic neuron K, then if both J and K are simultaneously excited, then the synaptic strength WKJ is increased. However, if two neurons on either side of a synapse are activated, this is actually unsynchronized, are activated unsynchronously, then the strength of that synapse is selectively decreased. That is, if J and K fire at different times, then strength of WKJ will decrease. Okay, and I hope that everyone is familiar with this notation, that is WKJ, where K is the postsynaptic neuron and J is the presynaptic neuron. Okay, now let us talk about some properties or features of Hebbian network. First one is it is time dependent. That is, the modification in the Hebbian synapse or weight of the Hebbian synapse depends on the exact time of occurrence of the presynaptic and postsynaptic activities. That is, as we have mentioned earlier, if the postsynaptic and presynaptic activity takes place simultaneously, then WKJ will increase. And if the postsynaptic and presynaptic activities take place asynchronously, then WKJ is going to decrease. Okay. Then the second feature is that it is a highly local mechanism. That is, the weight of the Hebbian synapse between two neurons A and B depends only on the activities of A and B. Okay, that is, no other neuron in the network will affect the WKJ or weight of the synapse between A and B. Okay, then the third property is that it is strongly interactive. This means that the occurrence of change in the Hebbian synapse depends on the activity levels on both sides of the synapse. In other words, we can say that Hebbian learning is based on a true interaction between the postsynaptic and presynaptic neurons. Okay. Then the fourth and final feature is it is correlational. Correlational means that the modification of the synapse is based on the co-occurrence of presynaptic and postsynaptic activities. Okay. Now we will talk about the correlational feature in more detail. Correlation can again be classified into positive correlation, negative correlation, and uncorrelated activities. Okay. When the presynaptic neuron and the postsynaptic neuron fires at the same time, then we can call it a positive correlation. And the positive correlation, as we know by the Hebb's hypothesis, will increase the strength of the synapse. Negative correlation occurs when two neurons are fired unsynchronously. That is, suppose there is a neuron A and another neuron B. If neuron A is excited, then the neuron B will be in a relaxed state. Similarly, when neuron B is excited, neuron A will be in a relaxed state. And as we know, negative correlation will result in the weakening of synapse. Okay, actually synaptic strength. And uncorrelated obviously means that it doesn't belong to both positive and negative correlation. That is, both the neurons are permanently in relaxed state. Okay, so we can compare this to the activity of two switches. Suppose there is a switch A which corresponds to neuron A, that is a presynaptic neuron, and there is another switch B which corresponds to postsynaptic neuron. Okay, so this is pre and this is postsynaptic neuron. Suppose both the switches are on, then it relates to positive correlation. Suppose one of the switches are on, that is when A is 0, B is 1, and when A is 1, B is 0. These two states corresponds to negative correlation. And uncorrelated is that when two neurons are eternally in relaxed state. Okay. So although we said that positive correlation leads to strengthening and negative correlation leads to weakening, we didn't say anything about uncorrelated state. So it is something that we can debate upon. Actually, the designer of the neural network has the liberty to decide what happens when the neurons are in uncorrelated state. That is, he can decide that when the neurons are uncorrelated, the synaptic weight should increase or decrease, or there is no change in the synaptic weight at all. Okay, so that's it. Now we will move on to the classification of synapse modification. Synaptic modifications can be classified into three types: Hebbian, anti-Hebbian, and non-Hebbian. In Hebbian modification, as we have already seen, the synaptic strength, that is WKJ, will increase with positive correlation. Okay, that is, when the neurons are positively correlated, its synaptic strength will increase. So, by this logic, what will be anti-Hebbian? Obviously, it is the opposite of Hebbian. That is, the synaptic strength WKJ will increase with negative correlation. Okay, that is, if the neurons are negatively correlated, then the synaptic strength will increase. And non-Hebbian obviously doesn't involve both a Hebbian or anti-Hebbian mechanisms. Okay, now we will move on to the mathematical model of Hebbian modification. We know that in Hebbian mechanism, the strength of the synapse or the modification of the strength of synapse, that is WKJ, depends only on the presynaptic and postsynaptic activity. That is, we can write delta WKJ as a function of Sj and Yk, where K is the postsynaptic neuron and J is the presynaptic neuron. Now, using the help of a rule called activity product rule, we can state this function as delta WKJ equal to eta into Xj Yk, where eta is obviously the learning parameter. Okay, and also we can see that the delta WKJ is a non-zero quantity only if both Xj and Yk are present, right? Therefore, what can we infer from this? That is, activity product rule shows positive correlation. Okay. However, there is a problem with this activity product rule. In order to explain that, let us draw a graph of delta WKJ versus Yk. So, this is delta WKJ and this is Yk. And let Xj be held constant. Okay. Now, we know that activity product rule is delta WKJ equal to eta Xj Yk. So this is an equation for straight line passing through origin. Therefore, the graph will look somewhat like this, right? Now, what is the problem with this? The problem is that whenever suppose we have a positive Yk, and correspondingly there will be a positive delta Wk, and we know that Wkj n plus 1 equal to Wkj n plus delta Wkj n, right? So a positive delta Wkj will result in a bigger synaptic weight, which will in turn increase the Yk. Therefore, the next time Yk will be over here, and this will lead to an increased delta wk, which will again lead to an increased yk. So when we plot a graph between yk and wkj, it is not delta wkj but simply wkj. Now let this be yk0 and let this be yk1, and let us draw one more, and let this be yk2. Similarly, this will be delta wkj0, delta wkj1 and delta wkj2. Okay. Now suppose this point over here represent the yk0. Okay, and this is the corresponding wkj0. In the next iteration, that is yk1, we know that for yk1 we know that wkj1 will be wkj0 plus delta wkj0, and we know that delta wkj is this much quantity. So in this iteration we are going to add this much quantity. As a result, the graph shifts from this point to this point. Let me denote this distance as a over here. So this much distance will be a. Now we are going to draw the next iteration, that is yk2, and for yk2 wkj2 equal to wkj1 plus delta wkj1, and we know that delta wkj1 will be this much. Let me denote this as b, and it will get added from this level, that is we are going to get the next point over here, and this will be b. And similarly in the next iteration, that is yk3, we are going to get wkj3 as wkj1, sorry, 2 plus delta wkj2, and delta wkj2 is this much c, and we can see that it is going to be over here. Okay, so if we draw this graph, it is going to increase like this without bounds, right? That is, after a few more iterations, the wkj value is going to reach levels which the hardware cannot process. So this is a problem with the Hebbian hypothesis. So in order to tackle this problem, we can modify the Hebbian hypothesis using these two methods. One is to introduce a forgetting factor, and second is to use covariance hypothesis. Now we will talk about forgetting factor in detail. We know the activity product rule as delta wkj of n equal to eta xj of n into yk of n. Now in this method of adding a forgetting factor, we will minus this expression with alpha yk of n into wkj of n, and let me take out eta yk of n outside. So it will come as eta yk of n into xj of n minus alpha by eta wkj of n, right? Let me rewrite this alpha by eta as some other quantity, that is c. Therefore this equation modifies as eta yk of n into xj of n minus c wkj of n. This equation over here is called generalized activity product rule. Now here we can see that when xj of n is greater than c wkj of n, the value of delta wkj is going to be positive, and when xj of n is less than c wkj of n, the value of delta wkj is going to be negative. Okay, and when xj of n is equal to c wkj of n, the value of delta Wkj is going to be 0. Thus, we have tackled the problem of ever increasing value of delta Wkj in the case of activity product rule, right? Thus, we have found a solution for that problem. Now, there is also another mechanism by which we can tackle the problem with activity product rule. That is called covariance hypothesis. In covariance hypothesis, instead of taking the activity product rule as it is, that is, instead of directly multiplying xj and yk, we are considering the strength of xj and yk over some averaged value. So, if we define some time average value of xj, that is xj bar, which is nothing but the mean of all xj's over a time interval of n, and similarly some time average value of yk, okay, that is the mean of the values of yk over an interval n. For example, the mean of xj will be x of 1 plus xj of 2 plus xj of 3 plus etc. up to xj of n by n. Similarly, yk bar also. Okay. Now we will modify the activity product rule as delta Wkj of n equal to eta into xj minus xj bar into yk minus yk bar. Okay. Now, if we plot this equation, that is delta Wkj of n versus yk, we will get something like this. Okay. This point here will be minus eta into xj minus x bar into y bar, right? And this point is called point of maximum depression. Okay. And this point over here is called balance point, and occurs when either xj equal to x bar or yk equal to yk bar. Okay. Now also you can see that it is not necessary that delta Wkj should increase all the time. It can take both positive and negative values and also zero values. Thus, it has a stability effect, unlike in the case of the activity product rule which we have seen before, right? Therefore, to summarize, you can say that delta Wkj will be positive if xj greater than xj bar and yk greater than yk bar, and delta Wkj will be negative if case A, if xj greater than xj bar and yk less than yk bar, and case B will be when xj less than xj bar and yk greater than yk bar. Now another question you might ask is, what if both xj is less than xj bar and yk is less than yk bar? That case is, in that case also delta Wkj is going to be positive. Why? Because here is also an n and here is also an n. Even though both xj and yk are less than xj bar and yk bar respectively, there is some positive value of xj and yk at the same instant n. What does that mean? It means that it is positively correlated, and according to Hebbian hypothesis, if two neurons are positively correlated, its strength should increase, right? Therefore, delta Wkj is going to increase when both xj is less than xj bar and yk is less than yk bar. Okay. Now, one more important question remains, that is whether the Hebbian hypothesis is supervised or unsupervised learning. So, what do you think? In this method, we haven't talked about giving any input pair and also the desired output pair to the system, right? We are simply giving only the input pairs and leave it to the system to figure out the output, right? Therefore, it is a method of unsupervised learning, right? Okay. And with this, we have concluded the Hebbian hypothesis. And if you have any doubts, please ask in the comment sections. Next thing we have to learn is competitive learning. Competitive learning, as the name suggests, the output neurons of a neural network compete among themselves for being the one to be activated. That is, unlike in the Hebbian hypothesis, here only one of the neurons will be activated at a time. Okay, I meant the output neurons. Only one of the output neurons will be activated at a time. So, in the competitive learning, all the input neurons, let this be input neurons, let this be output neurons. Okay, so in competitive learning, all the input neurons are connected to all the output neurons, like this, like this. Yeah, you get the idea, right? Okay, and each of these things have weights. Let this one be x1, x2, x3, x4, and this will be y1, y2, y3, and this will be w11, this will be w21, this will be w31, etc. We have to mark all the synapses. Okay, similarly the output neurons are also interconnected, like this and like this. However, unlike the case of connection between input neuron and output neuron, where all the synapses are excitatory, here the connections are inhibitory. That is, one output neuron is trying to inhibit the activity level of other output neurons. We can think of this analogy. Suppose we are in a class and we are all studying a same subject, that is artificial neural network, for example. We are all getting the same inputs, right? The same course material, the same teacher, the same class, etc. However, only one among us is going to be the topper after the exams, right? So, in the competitive learning is also similar to this. That is, only one of the output neuron is going to win, and only that output neuron will be activated at the end of an iteration. Okay. Actually, this will get more interesting when I tell this. We all know that one person in our class who, even though get a better textbook or better course material to refer and learn, he won't say it to others. Why? So that he has a better chance of becoming the topper, right? The same thing is happening between these output neurons. That is, one output neuron is trying to inhibit all other output neurons in the same way a guy who got the extra textbook is trying to win an edge over the others by not sharing the textbooks. Now, suppose that one of the students became the topper in the first test, okay? And now suppose that the teacher knows that this one particular guy is the topper. Although the teacher is supposed to be impartial, consider this case, that is the teacher is partial, and while evaluating the second test series, even though there are some mistakes for the topper, the teacher will think that he knows the answer, so let's relax this mistake for him, right? And he will again become the topper, right? This is going to happen in the case of competitive learning. That is, if one of the output neuron is the winner, then there is a higher chance for the same output neuron to be the winner in the next iteration also. Okay, and in this fashion, in the next iteration, there is an even higher chance for this neuron to win. Okay, now you get an idea about competitive learning, right? In simple words, this is how competitive learning works. Okay, we'll go into the details of the competitive learning in the next video, as the time for this video is already out of limit. Okay, so if you have enjoyed the video, please subscribe the channel, and if you have any doubts, please do ask in the comment section, so that I can answer that, and also I can keep note of that while making new videos. Okay, thank you.